All right, so we're going to start section 4.4. 4.4 is called the dot product. Now, you might not have been aware of it, but if you think back to what we did in the last section, we described how we add and subtract vectors, right? But we did not describe how we would multiply or even divide vectors. True? Okay. Well, the fact that this says product must mean that we're talking about multiplication, and we are. But the reality is that with vectors, there are two ways to find a product, and this is only one of them. This is the dot product. The other way of finding a product is not something that we're going to encounter in trig, but just so that you know what it's called the cross product, okay? So dot product's the only one that we are going to work with. And the dot product looks like this. So if we have two vectors, where vector 1 is AI plus BJ, and vector 2, W, is CI plus DJ. Then the dot product, and it is represented by a dot, so don't use any other symbol between them. It is not appropriate to just interchange symbols for multiplication here. It really is a dot. What we do is we multiply the components, coefficients from the I components, A times C, and we add that to the components, coefficients from the J's, B times D. Notice what happens when this happens. The dot product, oh, it's not written here, it's on your paper though. Note, the dot product of two vectors is a scalar. In other words, it's a number. At the very end here, we just get a number out of this thing. We do not get a vector. Okay, so a vector plus a vector is a vector minus a vector is a vector, but a dot product of a vector with a vector is a number. Okay, and we'll see application of what this is doing for us later, because it's not doing maybe what we would hope that it would do or all that we would expect that it might do, because we're getting a number, and that seems a little bit odd, right? It does. It seems like it should be getting me somehow a vector. Just for a fun fact, cross products do give you vectors. And again, they don't tell you exactly what you might think they would tell you either, but they do give you vectors. Okay, the good news is that finding dot products is pretty straightforward. It's just multiplication and addition, right? So that's actually what we're going to be doing on the next problem. We're going to find the dot product V times U and the dot product U times V, okay? So first, V times U, as directed, means I take the first component of V, which is negative I. I have no idea why those are in parentheses on problem number 1. They do not need to be. That's weird, but that's all right. Okay, so negative 6 is our first value. And I multiply that by the first component on the U, which is 2. And we're going to add that to the first component's coefficient on the J for V. I didn't say first component, the second component. So that's 1. And the second component, J's coefficient, which is a 3 for U. All right, negative 6 times 2 is negative 12. 1 times 3, of course, is 3. And if I add those together, I get negative 9. Okay, now the directions actually tell us here to find U times V next, which we will. So U times V would be taking the first component for U, which is 2, and multiplying it by the first component for V, which is negative 6. We're going to add that to the second component, which is 3 for U, and the second component for V, which is 1 over here. And lo and behold, did I write it backwards? No, I didn't. Yeah, negative 12, and then I have plus 3, and I get negative 9, and we notice that they are the same, and that should make sense. And the reason that should make sense is because the only thing that switched was the order of multiplication. And when we change order of things, that's a property for multiplication called commutative, right? Negative 2 times 6 is the same as 6 times negative 2, right? You flip the order and it doesn't change the values. So the order in which we do a dot product doesn't matter. In other words, what this tells us is that V dot U is equal to U dot V. And I know that feels like, well, doesn't that always happen? And the answer is no. It doesn't always happen that every property is commutative. And I can do a real quick one to show you why. If you did subtraction, the order would matter, right? If you did division, the order would matter, right? Yeah, so the fact that this works for dot products is not necessarily just a given. It actually worked because there's a multiplication component in there and it has the commutative property. All right, let's take a look at some more. They give us some vectors at the top here. U is given, V is given, and W is given. And then they ask us to find some dot products, but they also they tell us here that there is a coefficient on one of them. Now, we talked about what to do with that last time. Do you remember what happens when we have 4 times the vector U? What does it mean? Yeah, it's 4 times what? Okay, so as it's written right now, how would I find 4 times U, just that piece? Distribute the 4. Jamie, can you finish what you're saying? To the U components, right? So whatever the U components are, which they're up here, I'm going to distribute the 4 to each of the components, okay? So whether you could verbalize that clearly or not, I think all of you probably remember that from last time, right? Yeah. So what we're really going to be doing is we're going to be taking that I, which has a 2 on it, and now it's 8I, and that 5, and it's going to be 20J. And this is going to have a dot product with, I'm going to do it like this. Oh my goodness, I can't get my dot to work. There we go. Times the V. And V over here is negative 3I plus 7J. Now, Beck's already ahead of the game because he actually said something, whether he quite realized it or not, I'm not sure, that there's a fact here, but we're gonna see that here in just a second too, so hold tight to that thought. So what do I do for the dot product now? Okay, tell me what to do. Solve it. So what's my first step? 8 times, which one? Negative 3. Yeah, the I is multiply, and we're going to add. And then what do I have? Come on, Chloe, tell me. It's like you want to tell me, but you don't want to say anything. Tell me, what's going on? Well, so we're not going to have the 8 times 7. This isn't a distributive property, right?
You just multiply negative 20 and 7?
Yeah, you just multiply the negative 20 and the 7. Okay, so there is a tendency to look at this and say, it looks like I'm distributing, right? But this dot product, this is a dot product here, is not multiplication, correct? It involves some multiplication, but it's not multiplication. So if you want to think about this from the perspective, all we're doing is these 2 pieces. We're only doing the first 2 multiplied and the last 2 multiplied. And again, we ignore the i's and the j's, right? They eliminate themselves. It's just the coefficients in front of them that get multiplied. Okay, that's negative 24 and negative 140, which gives me a total of what? Thank you, negative 164. Audience participation, it'll make things go quicker. Okay, here's the deal though. Beck said something and he was absolutely right. What he said was, in case you didn't quite hear him, can we just basically multiply the 4 times what we had, hopefully from the previous problem? And we can. So the previous problem over here said that U times V was equal to negative 9, right? So these aren't the same U's and V's. But if they were, and we'd already done U dot V, right, the U dot V part, we could have just multiplied that by negative 4, or by positive 4. So let me show you that that works. Let's take U dot V first together and then multiply it by 4. Okay, so the U's and the V's changed, so we can't use the previous slide, but we can use the same principle. So I'll put the 4 in front, and let me just do the U dot V first. So here's the 2 and the negative 3, so I can do 2 and negative 3. And I can do the negative 5 and the 7, like this. Okay, everybody good so far? All right, so this is negative 6 and negative 35. What is negative 6 times minus 35? Negative 41. And what is, well, it's negative. What's 41 times 4? Yeah, which is the same thing. So we have the ability to do something that looks a lot like the associative property, where it says I can change the order of what's happening, not, like moving it like commutative, but I can do a different piece first. I can do the dot product first, and then I can do the scalar part second. But I could also do the scalar part first and the dot product second. Either way is possible. Okay, let's take a look at another one. So our u and our v and our w, I think they're the same from the previous problem. Yep, they are. And we're going to find each specified scalar, just like before. So we're going to do v dot u, and then we're going to do v dot w. Okay, so v and u are here. So v dot u means, and again, the order doesn't matter, which I do, right? I can do u dot v or v dot u. I just need to multiply the coefficients of the I components. So that's 2 and -3. We already did this before, but I'll write it in. Plus, and then u is -5, and the v is 7. So all of that is this first piece. Plus, and then I'm going to do v and w. So I have that same -3 showing up again, but now I have a -1 because that's the I component here, right? And I have the j component, which is 7, and the j component on the other one, which is -6. Okay, everybody good? Did I get all the pieces in there look okay? All right, so we have -6 and we have -35. This is the same -41 we did on our previous slide. Over here we have 3 and -42. So what is 3 and -42? Yeah, -39. So -41 and -39 is what? Somebody say. Thank you. -80. That's not a very good zero. Let's try again. But I'd like to show you something that you may have wondered about, and you may not have, and that's fine if you didn't. But did you notice that both of them had v in them here? Right? All right. Another option, because we're going to see as our concluding statement here in a minute some properties. Another thing that you might think of is factoring. You've done factoring. You've done factoring for me, right? Back in 3.5, it was maybe one of your least favorite things to do this semester. I'm not sure. Some of you definitely it was. But this v seems to be present in both pieces. And if this were just algebra, it would be the truth that we could take the v out and then we could just take the u and the w and we could add them, right? That would be an algebra property. And so let's take a look if we did it this way, if we'd get the same value, okay? So we're going to take a look at it from this perspective. So I'm going to leave my v on the outside for the moment and just write it as v. If I take u plus w, so u plus w, that's our last section that we just did. It means we just add the components component-wise, right? Just like algebra. So if I have positive 2i and negative I get what? I, right? Yeah, this is an I. There should be a dot right here. Let me put a dot right here and get that in there. And then if I add the j components, I have -5j and -6j. I get -11j. Okay, everybody good so far? Okay, so let me put the v in beside this now. It's -3i plus 7j. And remember, it's a dot product, not a distributive property, a dot product here. And then I have I minus 11j. Okay, so dot product says I only multiply, kind of like with the addition, I only multiply the I components together. So this is -3 and +1, right? And I only multiply the j components coefficients together. So this is 7 and -11. So the first one's -3, the second one is -77. And what do we get? -80. We get the same thing. Okay, this is the last slide I'm going to post. I would encourage you to write them down. These are the properties. We've actually explored the first one and the second one, and then the last two we'll talk about next time, okay? So the first one says that we do have dot products that are commutative, and the second one says that we can distribute or undistribute, i.e. factor, when we're working with addition and dot products together, Okay, so we will pick up on magnitude and zero vectors and explain why those should sort of make sense when we come back on Monday.